Okay, so we were on the topic of periodic property the other day, and we talked about so far two different periodic properties. Um, that's atomic radius, the size of atoms, and ionization energy. Okay, the energy needed to remove one electron from a particle. Okay, and now the third periodic property we're going to talk about here is called electron affinity. Okay, and what is electron affinity? This is actually having a little bit of relationship to the ionization that we just talked about. Okay, and ionization energy is the energy that is needed to remove electrons. So when you take electrons away from particle, atoms or ions, okay, you need to use energy. Okay, that process is a energy absorbing process. Okay, and now if you think about that process of removing electrons for the atom, it's an energy absorbing process. Then try to think the opposite. What if I'm trying to put a electron onto the valence shell, put one more electron onto the valence shell of a given atom or ion? Okay, and if taking away electrons is energy absorbing process, then releasing electron, the remove electron, is going to be an energy releasing process, right? So this is the amount of energy released when electron is added to the valence shell of a particle. So first of all, let's, just like the atomic radius and ionization energy, let's establish our trend. So let's say this is our periodic table. Okay. And again, from bottom to top, from left to right, and you would find that the electron affinity actually have the exact same trend with ionization energy. That's from bottom to top. The electron affinity value increased. That means more energy released. Okay, and from left to right, electron affinity increase. Okay, so now how do we explain this? Now, first of all, let's, although the trend is the same with ionization energy, I want to clear something up. That is, in this case, we're going to exclude, for electron affinity, exclude noble gas. The trend that we're talking about doesn't include noble gas. If you're wondering why, well, okay. When we are taking electrons away from ionization, to think about ionization energy, okay, everybody on the periodic table have some electrons. Okay, so you can always take electrons away. Okay, but when it comes to electron affinity, you're adding electrons. Now, remember, you're adding electrons to valence shell. Okay, think about these noble gases. At their valence shell, okay, they already have an octet. Okay, where are you going to put those electrons? Okay, are you going to put it in the valence shell d orbital? Are you going to put it to the next shell on the s orbital? Yeah. For this particular valence shell, you can't add anything right now. Okay, even if you just push it in, the atom would just simply wouldn't take it. Okay, and for other elements, okay, at least your valence shells still have some empty orbitals or have some room for you to fit your electron in. For noble gases, we don't have any room for it. Okay, so that's why we are excluding this. Okay, now, and then let's think about the trend. Okay, so let's, left to right, let's think about sodium and chlorine. Okay, so adding an electron in there, okay, how much energy will be released? Remember, every time energy released, that means lower energy means higher stability. Okay, now, so how does adding a electron into the valence shell matter to sodium and to chlorine? Because these are the two elements on the two ends. So we're talking about from left to right. Let's think about that. Now, for chlorine, this guy has 7 electrons in valence shell. Okay, if you add 1, you got an octet. What do we know about octet? Okay, octet is the promised land for all atoms. Okay, everybody wants it. Okay, and if you can give chlorine an electron, chlorine wants just 1 electron. Remember, this guy makes -1 charged anion. You just want 1 electron, and then you decide that you're gonna give it to him. Well, think about how happy chlorine is. Okay, if I get this 1 electron, I'm gonna have an octet. I'm gonna look perfect. Okay, and now I'm getting 1 electron. Now, why do they love octet? Simple. Octet is stable. And what do you mean by a structure, an octet structure is stable? Lowest energy. Okay, so from, this is high stability, okay, low potential energy. And how do you achieve low potential energy? Lots of energy released. So when you put 1 electron onto chlorine, because you achieved an octet, a lot of energy is released during that process. Now think about sodium. Guy has 1 electron in valence shell. Okay, when you add another electron in there, okay, each time you add an electron, okay, by default that you're going to release some energy. But is adding 1 electron matter that much to sodium? I want an octet. Okay, adding 1 electron, I'm getting closer to an octet, but it's still so far away. 2 electrons, I'm still 6 away from an octet. So yeah, I'm going to release a little bit of energy, but don't expect me to jump up and down for getting this 1 electron, because I'm still way, way, way away from octet. Okay, so not much energy released. Okay, so now bottom to top, think about between sodium or lithium, and let's say cesium. Okay. Now, if you gave sodium one electron, remember that one electron is going to be on the third shell. Okay. So at least it's closer to the nucleus. Okay. Now, and if you're giving it to cesium, okay, that electron is going to be so far away. And remember, the cesium have way more electrons than sodium. Sodium has 11. Okay, giving him one, he has 12. Okay, that's a substantial increase in the amount of electrons. Cesium, number 55. That one electron is in the sixth shell. It's going to be so far away from the nucleus that you put one electron in there, the whole atom doesn't really feel much different. Okay, when you put one electron in sodium, at least going from 11 to 12 and having the electron number change in the third shell, okay, it affects the electron essentially more. Okay, so less energy, even less energy released, because it doesn't really affect cesium that much. Okay, and in that sense, you can say, well, okay, what about chlorine and bromine and iodine? Okay, chlorine would be pretty happy, okay, when you gave them one electron. Iodine, bromine and iodine is probably going to be less excited when you gave them. They're still happy, okay, they are getting an octet. But that octet, again, is so far from the nucleus. It's much more on the outside. Okay, so less energy would be, they're less excited, so less energy would be released during the process. And in that sense, now, following the trend, which element do you think on the periodic table have the highest electron affinity? And if your guess is fluorine, then you're right, because we're excluding noble gas. So the furthest on the right we can get is the halogen group, and fluorine is the one that's sitting on the top. So fluorine is the element that has the highest electron affinity of all elements. This guy gets one electron. He's really, 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 really happy. Nobody is happier than fluorine when it comes to getting an electron. Okay, and remember when we were doing oxidation numbers back in redox part, we said that fluorine in compound is always -1, right? We didn't say chlorine is always -1. We didn't say anybody else is always -1. Fluorine is always -1 because fluorines want that one electron so much that nothing else matters. Okay, so when you gave him that electron, he's the most excited, the most amount of energy is released. Yeah. So that's how electron affinity is. Yeah. All right, so the last periodic property we're going to talk about here is called electronegativity, or EN. Yeah. Okay, so what is this? Yeah. When it comes to electronegativity, in a way, is actually having some relationship with electron affinity, because it's all about getting electron. Okay, but when we talk about electron affinity, we're talking about adding an electron onto an existing atom or ion, and it's all about a single object. When we talk about electronegativity, okay, we're actually talking more about a chemistry bond. Okay, when you have two atoms competing for electrons. Okay, yeah. So this is the ability, representing the ability to attract shared electron pairs. Okay, yeah. And it's not about energy, it's not about, this is actually a defined value and not a measurable. Because energy, like ionization energy, electron affinity, those are amount that you can actually measure. Okay. Electron negativity is not a measured value. This is a defined value. People just slap a number onto a given element representing its ability to attract shared electrons. Okay, and the value is usually between 0 and bigger than 0 and less than 4, less or equal to 4. Okay, and this is representing the ability, okay, of a atom to attract shared electron pairs in a bond. And now, again, let's do the trend. And one more time, the trend is the same with ionization energy and electron affinity. And increase from bottom to top, increase from left to right. And again, we're going to exclude noble gas. Why do you exclude noble gas? Well, what do we need electronegativity for? To identify the ability to attract shared electron pairs in a bond. When do we make a bond? When you try to make a compound. What about these guys? Noble gases, they rarely make chemical compounds. Okay? They don't like forming bonds with people. They don't like share electrons with people, with other atoms. Okay? I'm already perfect. Why do I need you? Yeah. And so, in that sense, what's the element on the periodic table that having the highest electronegativity? You guessed again. It's fluorine. Okay, actually, this 4.0, this upper limit of electronegativity at 4.0 is actually defined on fluorine. Fluorine has a electronegativity of 4.0. Okay, now, and okay, now that you explain this number, why do I need this number, and what could I use this number for? Okay, and now you could use this number to actually determine when two elements making a chemical bond, okay, whether it's a ionic bond or it's a covalent bond. Okay, what do you mean? Well, think about it. Each element, okay, would have different ability to attract electrons. Okay, when you put two elements together, okay, and why would they share electrons? So we're actually going to be talking about a lot about that when we get to the next topic, which is Lewis structure. We're going to talk about some details, but eventually, all of these elements, okay, they try to get to octet, and when they couldn't, okay, they need to find a way to compromise, and that way to compromise is to bond with other elements by sharing electrons, okay, to achieve octet. Now, But if they share electron, okay, those shared electrons, how much the two nucleuses are attracting them, majority of time is different. Okay, sometimes two atoms could equally share a pair of electrons if their ability to attract electrons are the same. Okay, so now in that case, we say the difference of electronegativity between the two elements. Okay, in that case, same ability means same electronegativity value. Okay, so when the difference between the electronegativity of two atoms is 0, okay, we're saying this bond you made is a pure covalent bond. Okay, and a pure covalent bond, the easiest way to identify it is that it exists in elements, in molecules like hydrogen gas, oxygen gas, fluorine gas, chlorine gas, so on and so forth. Okay, because when you have two of the same atoms sharing electrons, of course their difference of electronegativity is 0. Okay, and in that case, your electron pairs, electron pair or electron pairs, are equally shared. Okay, and now majority of the time when you have two different elements making a bond, okay, you would see the delta En, okay, be a number that's bigger than 0. Okay, but what if their difference is actually pretty small? There are difference, but their difference is not as big. It is not crazy big. Okay, and in that case, the bond we call them polar covalent bond. Okay, things like HF, okay, HCl, okay, the bond between carbon and oxygen. Okay, now these guys, they're different elements. They have different electronegativity, but since they're all nonmetals, okay, their electronegativity difference is not going to be that huge. Okay, and in that case, they still share electrons. Okay, but your electron pair or electron pairs not equally shared, but still shared. Okay. Now, what if you have two elements that's having huge electronegativity difference, delta En? What if it's bigger than 2.0? Okay. Yeah. Well, imagine if you have two elements. Okay. They're trying to compromise, they're trying to make a chemical bond so that they can get octets. But then one element realizes my ability to attract these electron pairs are so much better than you do. Okay? If one atom can have that, what do you think it's going to do? Well, he's basically going to go, give me that pair of electrons. I'm stronger than you, I'm more attractive than you, and I'm going to take those electrons, and there's nothing you can do about it. Okay? This is the word of the atoms. Okay? There's no moral there. Okay? It's the jungle. If I'm stronger, if I'm have higher attractive ability, strong attracting ability, I'll take those electrons. And once, let's say, this guy, the stronger, the higher electronegativity element, like fluorine, completely took the electrons, then what do they turn into? Well, they take extra electron, they turn into negative ions. Oh, okay, so now you're talking about ionic bond. And this usually happens between things like sodium and fluoride. Okay. Barium and chloride. And the list can go on and on, okay? This normally happens between metal and non-metal, okay? Because if you look at the periodic table, okay, electronegativity increase from bottom to top, left to right. What are the elements at your bottom left? The ones that having the lowest electronegativity? Metals, okay? Now, what's the elements around your top right corner? This is where the non-metals are. Metals tend to have low electronegativity. Non-metals tend to have high electronegativity, and their electronegativity difference, of course, is going to be bigger. So that's how electronegativity work. And no, okay. So for these three later periodic properties: ionization energy, electron affinity, electronegativity. No, okay. No. All three of them have the exact same trend: increase from bottom to top, increase from left to right. Okay, but explanation of each is slightly different, and we also know that two of them, ionization energy and electron affinity, are measured values, and electronegativity is defined value. And for electronegativity, we typically only use it to determine to estimate what kind of chemical bonds we're making between two elements. All right, so the next thing that we're going to talk about here, start another big topic here. Lewis structure. Okay, and now, first of all, what is this? Well, now that we know so much about individual atoms, their electron configuration, their love of octets, and this is the time that we take another look at all these different compounds that we learned, okay, and try to think, okay, how did these different atoms, you tell me one molecule, okay, made up by a whole bunch of different atoms, okay, how they're bonded together. Okay, we know bonds are sharing electrons, so how do they share? Why could they share it this way? Okay, and how many pairs of electrons need to be shared? Now, these are the things that we're going to be discussing here. Okay, now, before we talk about Lewis structure of molecules, now first let's go to something one step lower. Now, the Lewis dot symbol. Okay, now what is the Lewis dot symbol? Now, this is element symbol plus dots that represents valence electrons. So what do you mean? Well, using typical elements on the periodic table as the example, if I have lithium, if I want to show the Lewis dot symbol of lithium, I'm going to put one dot right beside it, representing on the valence shell of lithium, you only have one electron. Okay, and if you have things like magnesium, okay, I'm going to put two dots in for magnesium to represent the two valence electron for magnesium. If I'm having aluminum, I'm going to use three dots to represent the 3 valence electrons of aluminum. If I'm doing oxygen, I'm going to use 6 electrons to represent the 6 valence electrons of oxygen. Now, if I'm going to have fluorine, I'm going to have 7 valence electrons. If I'm having krypton as a noble gas, I'm going to have 8 dots as valence electrons. Okay, and now, why do we want to do Lewis dot symbol? Because it makes our initial period of understanding how the electrons interacting with each other. Okay, it makes that process easier to see, and it helps us to make sense out of them. Okay, so with the Lewis dot symbol, let's think about how molecules work. Let's start from the easiest. Now, H2. Okay, so essentially you have 2 hydrogen atoms, and I'm going to use 2 different dot symbols to represent, because they're different atoms. They only have one electron, and now I want you to be able to differentiate the 2 atoms. All right, so let's say you have hydrogen atoms. Okay, now obviously hydrogen, like everybody else, wants to turn into a noble gas electron configuration, but hydrogen is in the first row where it only has hydrogen and helium. Okay, so its noble gas electron configuration is not exactly an octet. It's actually helium with 2 electrons. Okay, and this hydrogen is going, okay, like I'd love to get another electron to turn into a helium electron configuration. Okay, if I can find a metal like a sodium, I can probably turn into a metal hydride, H negative ion, to achieve that. But looking around, there's no metal cations available. Okay, so here comes another hydrogen. And these 2 hydrogen looked at each other and go, okay, I probably won't be able to rob him. He's about the same strength with me. Okay, now I have 1 electron, he have 1 electron. If he's going to try to take my electron, I'm probably going to fight with him till the end. So if I'm going to try to take his electron, it's probably the same result. It's not worth it. But I also know that he wants that helium structure with 2 electrons, like crazy as well. So let's see if we can negotiate this thing out. So these 2 hydrogens sit down together and go, okay, I'm going to take my 1 electron and put it on the table in the middle of us. You do the same. So now, since we're both sitting at this table and the electrons now is sitting on the table, okay, both of us can say, well, I have 2 electrons now. I have a noble gas electron configuration. And you can say the same thing. I have 2 electrons surrounding me now. I have a noble gas electron configuration, just like helium. Okay, so in this case, once they share this pair of electrons, are they going to leave each other? Hell no. I only got 1 electron, and my one electron is on the table. I'm not leaving the table. And the other hydrogen is saying the exact same thing. Well, 1 pair of electrons shared, you got a H2 molecule. Makes pretty good sense, right? And now, similar things could happen to hydrogen and fluorine. Okay, hydrogen has 1, fluorine has 7. Okay, and they go, well, our electronegativity difference is not that big. Fluorine can rob a metal pretty easily, but probably not hydrogen. Okay, hydrogen is a non-metal. It's pretty strong in holding on to its electron as well. Okay, so now what they do? Then hydrogen and fluorine decide that, okay, I'm going to put one of my electron out. You put one of your electron out. Now let's share. I can say that I have 2 electrons with a noble gas electron configuration, and you can say you have 8 electrons. You have a perfect octet. Both of us are happy. We get a molecule. All right, so sharing one pair is pretty simple and straightforward. Now, what about this guy? Okay, so let's see. Oxygen. One oxygen has, we already did that, 6 valence electrons, so 6 dots. And this oxygen obviously wants 2 more electrons to get an octet. Okay, so if it could find a calcium, a barium, he's going to be extremely happy because it's easy. If he can find 2 sodiums, he's going to be happy about that as well because he can take 1 electron from each of them pretty easily. But this poor hydrogen looks around and don't see no metals. And then he saw this other oxygen. And you got to think about this, okay? I probably can't rob him, okay? Exact same butte, exact same strengths, exactly same ability to compete for electrons, okay? So, but then they look around, they saw this hydrogen molecule or that hydrofluoric acid molecule. Okay, they shared and they got noble gas electron configuration or octets. If I can't directly take these other oxygen's electron, can I share with them? And the other oxygen is thinking about the same thing. But of course, both of them realize that if I'm only sharing one pair with you, then neither of us is getting an octet. Okay, because that means sharing 1 electron means adding 1 electron to me. I have 6, adding 1 is going to give me 7 electrons. Who the hell needs 7 electrons? I want 8. But no problem. I have another electron. You have another electron. Let's share that. I have an octet. You. Oh, sorry. Shouldn't have that. I have 8. You have 8. Let's clean it up. Now. Okay, and then if you understand how oxygen made it work, you definitely understand how nitrogen made it work. Okay, nitrogen has 5 valence electrons. Okay, and now how is it going to bond with another nitrogen? Okay, sharing 1 pair of electrons is not going to be enough. Sharing 2 pairs of electrons is not going to be enough. And these 2 nitrogens decide that, okay, hell with it. I'm going to share 3 pairs of electrons with you. I'm taking out 3, you take out 3. You can still keep a pair, I'll still keep a pair. But now, oh, damn it. I have octet, okay, 2 plus 6, and you have an octet, 2 plus 6. Both of us have octets, and we're happy. And now you can see, okay, why nitrogen is one of the most stable gas that's available. Okay, it's going to be very, very hard for you to break the connection between 2 nitrogen atoms in an N2 molecule. Why? Look at how much electrons they share. They share 3 pairs of electrons together. Okay? imagine how much harder it is going to be if you're trying to break it. Okay, be way harder than hydrogen, way harder than HF, way harder than even O2 gas. Okay, because you need to separate 3 pairs of electrons to turn this thing into into 2 individual atoms. Okay, so now this is how we use Lewis symbol. But once we get comfortable with Lewis symbol, okay, now we realize that, okay, like making all these dots, okay, are too much trouble. And you have 2 atoms in these molecules, and you're already using 2 different types of dots to track how it works. Now, what if my molecule has like 6, 7, 8 different elements, all bonded together? Are you going to find 6, 7, 8 different dot symbols and then trying to play with all this? No, that's too much trouble. Okay, I'm not here to waste time on that. No. Okay, so this is where people realize that, okay, maybe, just maybe, okay, I don't need to use these dots. What do you mean? I'm going to try to use dashes to represent electron pairs. And you can see in each of these situations, okay, you would have electron pairs. Electrons are paired up. Okay, whether it's shared or it's belong to just one of the bonding atoms, electrons comes in pairs. All right, so each pair of electron is if it's replaced by 1 dash. Okay, each dash represents one pair of electron. And then how do you do O2? Oh, 2 pairs of electrons shared. There you go. What about N2? 1 pair, 3 pairs shared. And once you use these dashes to replace all the different dots, now these structure here, we call them the Lewis structure of molecules. Now, after we discuss and you practice, okay, by the end of the semester, I expect everybody to be able to draw the Lewis structure of a given molecule. Okay, now how do we draw Lewis structure? Just like balancing redox equations, okay, where I gave you a 7-step or a process, okay, or 8-step process, based on whether they're in acidic condition or basic condition, okay. Now, and just like that, okay, we're gonna give you a procedure of drawing Lewis structure. Okay. Step number 1 is count number of valence electron in all atoms. Number 2, determine a skeleton structure. Now, essentially saying, trying to determine which atom is bonded to which other atoms. Okay, so couple rules of thumb here is that first element in the chemical formula, is usually the central atom. And then B is hydrogen can never be central atom. Why? Remember, hydrogen only wants how many electrons? 2. Okay, and 2 electrons is 1 pair. If your element only wants 1 pair of electrons, you won't be the central atom. Okay, you can't. There's nothing central about you if you can only make 1 pair of electrons. You can only accept 1 pair of electrons. Okay, and then step number 3 is place 1 pair. Once you get your skeletal structure, place 1 pair of electron in each bond. Okay, now, and then number 4. Now, in the case of step number 3, now after you place 1 pair of electron in each bond, chances are you're gonna still have some electron left over. Okay, and the thing you do with those leftover electrons is give non-central atoms octet. Okay, and step number 5, any leftover electron goes on central atom. Okay, and number 6, if after all these previous steps, if central atoms do not have octet, then at this step, must form multiple bonds. Okay, what do you mean multiple bonds? Well, this is what I mean multiple bonds. Bonds that share 2 pairs of electrons, bonds that share 4 pair of electrons. The one that was 2 pairs of electrons, we call them double bond. The one with 3 pairs of electrons, we call them triple bond. Okay, so once we understand these 6 steps, on our next lecture, we're gonna do Lewis structures on quite a bunch of different elements, different molecules. And that's it for today.